Okay, again, if you have any question or if you cannot hear me well, you can feel free to interrupt me. And you can just unmute and interrupt me and let me know. Okay, all right. Okay, so in the last lecture, we talked about the introduction of parallel computing and introduce taxonomy from the hardware and software point of view for parallel computing. And so today we will talk about supercomputer as example of how a parallel computing system can be built for performance. And we can use it to introduce a few technology, in terms of hardware and software, how they can be optimized for parallel computations. Okay. So what is a supercomputer, right? In terms of the hardware, of course, it consists of many machines, and it's usually you have those. Each machine is called a server or a node. Okay, and different from the looking of a personal computer. Usually those servers looks like a slice, so you can put on a rack. Basically just like a bookshelf, but you can slice into those servers, and so you can use the space more efficiently, right? But the server is just like normal computer. It still has its own CPU, memory, and disk, etc. So to provide the computing power, like we mentioned, not only we need to we use CPU, but also we usually use some accelerator, okay, like GPU. So each server can be quite powerful alone, but still we usually have hundreds of servers in a single parallel system. So specifically, what is a supercomputer? It's actually represent a certain type of parallel computers that is specific design for performance. Okay? So any computer, if you design for the purpose of performance, you can say it is a supercomputer. But of course, in order to convince people, or to really show you have high performance, your performance need to measured and compared. So the measurement for performance, especially for supercomputer, is what we call the flops, floating point operations per second. So it's the number of floating point operation, like addition or multiplication, you can perform per second. Okay. So why we use it instead of other performance metrics is because of the application runs on those type of computing system are usually determined by the performance, usually determined by the flops, because those applications usually are mostly involve floating point operations. As we will see, those applications are usually for simulation, or for those computation driven by those matrix operations, etc. So flops is the closest performance metrics that can represent the real performance of this type of application. That's why we don't use other metrics such as MIPS, right? Because median instruction per second is more a performance metrics from the hardware aspect. It doesn't necessarily transform to the real performance experienced by the user. So the user cares about his application performance. Right? And so It can be measured, and it also need to be compared, right? In order to to claim you are supercomputers. So the real supercomputer need to be compared with all the machines in the world. So we have this top 500 list, announced every twice every year in the conference of a high performance community computing community. So they have this benchmark called HPL. Okay. So what is a HPL benchmark? As mentioned, right, the purpose is to measure flops. And specifically, the HPL benchmark implement a very simple application. It is an application that try to solve a linear matrix equation, just like what we show over here. So this is a very simple equation. However, of course, all the variables in these equations are floating point. And in order to solve this equation, right, you need those floating point operations. So this benchmark basically, the way to use this benchmark is you will use your computer to solve this equation. And doesn't means if runtime shorter doesn't means you have a better score. The score is calculated by flops, right? Floating point per second. So you can solve this equation for a very, very long time. As long as during that time, the amount of computation you perform, the flops, right? You divide it by time, the computation divided by time is the highest. Then you get the highest score, okay? So in fact, when people use this benchmark, usually they prefer to increase the problem size of this benchmark. As you can see, this calculation, those variable like R, right? Like A and B, they are the matrix. They are matrix, and the length of the dimension can be adjusted, right? The dimension is measured by n, right? The lowercase n. So that is actually a configuration when you run the benchmark. So you can adjust the size of your matrix, okay? And usually the larger matrix, the larger problem can give you a better performance in terms of flops. Why is that? Because in order to get the highest performance, you want to utilize all your resources, right? Such as your memory, your cache, or your computing cycle. So usually you need to increase the matrix size so you can fill in your cache and the memory space, so you can get a better performance. If it's too small, right, your computation is very short, then your performance will be low because you will suffer from some constant initialization time, right? Constant overhead. So usually you won't get a better result by solving a smaller size problem. Okay. And of course, if you make the problem size too large, also you may not get the best performance. Because, for example, if your cache is not enough, then if you keep increasing the problem size, then you will probably increase the cache miss rate, right? And then your performance can also goes down. So, in fact, in order to get the best performance or benchmarking score, people actually need to tune the parameter. And the size of the matrix is just example. Actually, there are a couple of more parameters you can adjust for this benchmark. And the reason it allows people to adjust, because depends on your hardware architecture or system design, right? You may get the best performers for different, under different condition. So people can adjust those parameters to, to allow your computer to perform the best you can. So there are some flexibility for you. Okay, so tuning those benchmark is one of the things when people try to run it. That's one of the issue or one of the step they need to consider. Okay. All right. So, but in any case, you can see they hope, if you get the better flops, that means you can solve a problem that involve this kind of computation, to more. So, so this is how people design the benchmark. Basically, benchmark is important because supposedly, if you can get a grammar, right? If they usually optimize their hardware and software to get the best benchmark score. And of course, we want to this result, this performance can actually apply to all the users in the real application. So the reason they pick this specific linear metric equation is because this is the type of computation mostly exists in those scientific computing system or scientific application. Okay? So the design of a benchmark is important. And you will see there are many kinds of benchmark exist for a different type of computing system. For example, deep learning is become very popular this day, right? So right now we are also having those benchmark designed for deep learning. And so if you have if your supercomputer perform very well on the HPL benchmark, sometimes it doesn't get very good performance or the same performance for deep learning, right? So that's why it doesn't guarantee. No, it is designed for deep learning, for example. Okay, so people usually depends on what's your target application. They will pick different benchmark, and they will follow that to optimize the software and the hardware, and so that the user at the end they can actually get the benefit from your performance. All right. So so as I said, how to get the best performance out of a computer system, right? It depends on many things, and a lot of techniques needs to be applied, not just hardware but also software. And more than that, sometimes you also involve system tuning, right? Including the tuning of the benchmark itself, like we mentioned. But of course, in your software and hardware, all the layers, there are definitely their own configurations can be tuned as well. And in order to achieve the best performance, all those things should be considered and optimized. And at the end, the cost, right, in terms of money and the power needs to be considered as well. So for supercomputer, as a fact, not only we have this top 500 list, we also have another list called the green top 500 list. So for that list, the performance actually what they compare is performance per watt. So the energy will be be included in the consideration as well. Okay, so because at the end you have to pay for what you compute, right? And so cost efficiency also is an important factor. So in order to achieve the best performance is really not easy. Okay, it requires hardware, software, engineering, and the money as well. And so it's actually a competition across the world and between nations, because many technology today is driven by supercomputer. If you follow the news recently, you will see right between country that have all the rules and all the all the politic consideration So they don't want this technology, right, to be used by other country to power their military or their economy. So you can see computing power is really important today. Okay. So the top 500 list is a competition without a doubt. And you can see from the list, you can roughly see, right, what are the countries that they control the technology, or they possess the computing power to drive their technology and economic. And here we just show you, this is the list from last year. I haven't updated to this year yet. And the list is always changing, okay, year by year, because all those countries, and they do invest a lot of money and time to show, right, they have this computing power. And also they build those computing systems, supercomputers, to continue drive their technology development. Okay. So right now, actually, the #1 system, I believe, is taken by United States again. And before that, all the machines you see right here has been one time to be the #1 machine in the world. Probably not long time ago, but they quickly get replaced by another system, probably just a few months. Usually, it's very hard for them to occupy the first position for more than a year or more. Okay. And as we mentioned, it's measured by HPL, right? This benchmark, and the result is indicated by the R max, that column. Okay. So R max is the performance, the petaflops. By the way, the unit here is petaflops, not teraflops or gigaflops. So the number here is really astonished. Okay, because a single computer usually just a couple of gigaflops, but this system, right, a single supercomputer can deliver petaflops computing power. So you can see those are very powerful machine. Okay, and R max is the number you get from the benchmark, and R peak is the number you get from your hardware spec, right? Because depends on, for example, how many machine you have, how many CPU core you have per machine, and what's the frequency or instruction per cycle of your CPU core. Follow those, you can compute the your ideal flops performance. But it's ideal because you only consider the raw computing capability. But in a real world, in an application, even it's as simple as the benchmark problem we saw, you still have many other overhead, right? For communication, initialization, or synchronization. So of course, it's hard to reach the R peak, the theoretical performance. As a matter of fact, you can see if you can reach 60 or 70% of the ideal number is considered to be pretty good. Okay. And another thing you can observe from here is basically all of them, they are using accelerator, right? Because this type of computing device or processor can provide much more computing power than the traditional CPU. So basically, you can see all of them have GPU installed, right? Whether it's a V100 or P100, all those accelerator. Okay. However, you will see #1 and #4 machine, they don't have an accelerator, right? However, the number of core is huge. So that means although he doesn't have an accelerator, but their processor or their CPU is different. They are not using the regular or the traditional CPU. Those are customized processor. So they are already their architecture is similar to GPU itself. So it's even a more tightly integrated processor, integrate the GPU and the CPU like chip together. Okay, so so that's why his core is a lot more than others, because those core is more like the GPU core. Okay? And another thing is, you can see another evidence of how important those accelerator is. You can see the number 15 machine, the machine from Switzerland. It get upgrade after 2016 on their accelerator. Before, they were using an older GPU model called K20X. And they didn't change the machine at all. They simply replaced this GPU card to the new model P100. Then you can see their R max and their R peak, right, increase almost more than triple. So you can see how how much performance can provide it from those accelerators. So of course, GPU programming is important. It's one of the most important part in this course as well. Okay. All right. So however, you will also see, right, those type of processor, those specialized processor or accelerator, they usually only fit, or they already designed for specific type of computation. So it's not like it's not like you can always take advantage or utilize those computing power. So still we need CPU, and still we need to optimize the performance for CPU systems as well. Okay. All right. And so we will give an overview, okay, of the trend from the top 500 list. You can see all those things on the website, or you simply Google for top 500, and then you will see their website, and they post all kinds of interesting number, from those supercomputers. And from those numbers, you can see or observe the trend of those hardware technology or computing system design. Just like the trend of using GPU, you can clearly see that. So for CPU, you can see today, right now, still is mostly dominated by the Intel CPU. But I believe you will see the percentage for AMD CPU will probably increase a lot, probably from this year and the next few years as well. So this just the trend also get changed over time. And for the interconnect, also is dominated by the interconnect called the infinite band. So some of you, or probably most of you, probably haven't heard or used infinite band before. What you use today are usually the Ethernet, right? I believe everyone knows what Ethernet is, right? This this kind of network cable and switch. Okay. However, for supercomputer, people usually use infinite band, and the reason is, of course, the performance of an infinite band are much better than the Ethernet. Okay, the reason is the way the technology. Okay, when he transferred the packet, he used a different way, and we will introduce that later. So we will leave it for here. As you will see, infinite band is also the mostly used interconnect for those supercomputers, especially for the one that rank higher. Because communication is definitely the main performance bottleneck for parallel computation. So if you can improve your network performance, then the overall system performance will be much better as well. Okay. How about the vendor? So the next interesting number is the distribution of the vendor who developed those supercomputers systems. Okay, so actually the highest rank vendor, the most famous one actually is Cray and IBM. Especially IBM, I think most of you know this company already because they have all kinds of products, right, including PC, laptop, etc. But Cray is actually the real first vendor or company that develops supercomputer. The first, no, the first generation supercomputer is from Cray. So until today, he's still one of the biggest player for supercomputer. Okay. And however, another interesting trend you can see over here is the increase of the company or vendors from China. So they pick up the pace very quickly, so quickly that some country realize it's a kind of a threat. So it's a real competition now, just not like a single country dominate the market now. You can see the percentage from those Chinese company, they increase very rapidly in the past decade. Okay? And for Japan, also, it's also one of the important country here, especially right a year ago they developed this fattest number one machine in the world. So of course the percentage also increase a lot in the recent years. Okay, especially notice this percentage, okay, is calculated by the performance share, not in terms of the number of machine. So that's why so for Fujitsu, he's also a very famous company. So he also one of the earliest company to develop those supercomputer and processor by their own. So the performance share for Fujitsu also increased a lot, because of that top rank machine. Okay. All right, so yeah, as I mentioned, right, so this is the percentage in terms of the machine, okay, the total performance share between those machines. And you can see that, so you can see that almost China and American are equal right now, and also Japan, because of the top rank machine, they are right next to them. Okay. All right. You can see this is a national competition, right? All the countries, they are investigate lots of money and human resource to not just own a supercomputer, but be able to develop their own supercomputer. So what's the end to this, right? Why we need to keep increasing computing power? Why we need to spend so much, right, resources to build those machines? And what's the performance we really want to get, right, by doing this? Okay. So at least for now, one of the clear goal to it is to reach the access scale. Okay, so what's the access scale? It means you can achieve a one access flops. Okay, basically is 1,000 times more than petaflops, basically a scale above. Okay. So if you can achieve that, that means you are doing the access scale computing. Okay. So when we say access scale, basically referring to, right, the dream or the goal to reach that level of computation. Okay. And why is access scale, right? What happens if we build such machine? So this is actually one of the goal from United States, is the national project called the Human Brain Project. It's a target from that national project. The reason, so the motivation behind it is they're assuming that if we want to do any real experiments in the level of a human brain, then exascale computing is the level of computing power is required to do so. Okay, so you can see it's enable you to do the next level research or technology development. That's why they set this scale, and they want to reach that scale by 2020. And as you know, we are already at 2022. But as far as the top 500 list goes, you can see the performance, their performance really grows fast year by year, but still not fast enough, right? So people still pushing very hard to increase the computing power of our machine, enable to reach this goal. And by the rate we have, although we haven't reached that goal yet, but I don't think it's not that far distance. All right, so that's just an overview of the supercomputer. And now, of course, more importantly is we will look inside it, right? How it can get such a performance. And of course, the reason is hardware, software, and not just for computing, but also for networking and storage and I/O. So of course, for this course, we only try to optimize our performance by optimize our code, right? Because we are only a programmer. But this part is to let you know that in order to reach the highest performance, mostly is not just programmer, not just your program, but the whole system. Okay, so the whole industry, the whole high performance computation community have collected efforts to build those systems, including providing those programming language and for user to write those parallel code. So you require all those efforts, and although we don't have a chance to get into those software hardware optimization, but at least we can introduce the technology, right? They develop for reaching this goal. So, right, for computation, of course, that's today, as you know, we rely on those accelerator, and specifically and mostly rely on GPU, right? And the reason is the architecture of GPU, as we introduce the SIMD architecture, can scale better than the CPU architecture. So the performance, the computing power of GPU can grow much faster than CPU. So that's the best way right now to gain more performance without a doubt. And here just show some number, and you can just look at it. So you can see the most important number definitely is the G-flops, right? And you can see the Tesla V100, right, which will be faster, right, 10 times. Actually, V100 is not even the latest model. So the latest model will even much faster than the CPU. Okay? And the reason, of course, because it has a lot more cores, right, than CPU, although it operates at much lower frequency rate. Okay? Another important thing is the memory bandwidth. Okay, so you can see we have this memory bandwidth. Specifically, we're referring to the internal memory bandwidth, because GPU has its own GPU memory inside. So within a card or even within a chip, then you can have a much more memory bandwidth. So you can feed much more data to your computing core to utilize those computing power. Okay. However, the drawback is that the size of the memory will become smaller, right? So for CPU, our host memory can easily go to hundreds of gigabytes or a couple of terabytes. But for GPU, even the latest technology, is only less than 100 gigabyte. So the amount of data can be stored temporarily on the card is limited. And in this core, in our CUDA programming part, you will see most of the optimization is about data access, how to utilize the limited memory space more efficiently in order to reduce the memory transfer and memory copy time. All right, and the last column is Xeon Phi. Not sure if everyone knows, but if not, it's a solution from Intel. And it's a solution between CPU and GPU in terms of their hardware or processor architecture. So you will see the numbers are sits between the two. But it has its own advantage. For example, on the Intel Xeon Phi, you can actually install an operating system on top of it. So it's like a computer inside a computer. And also, if your code can be compiled and run on an Intel CPU, then it can also be compiled and run on the Xeon Phi without any code change. So it has its own unique advantage. All right, and this is just a close look at the GPU. We won't introduce too much because we will see it again when we talk about the CUDA programming. But as I said, you can see inside the GPU down below, you have a global memory, right? So that's the memory we mentioned, right? The GPU memory. The internal memory bandwidth means the bandwidth between your processor core to this global memory. And you can see because within the GPU card, you have so many cores. So in order to manage and control those cores more efficiently, the hardware architecture is a hierarchical architecture. So those cores are actually grouped into the string processor. So a GPU card, inside a GPU card, you actually have multiple processor called the string processor. And each processor you have individually has many more cores inside it. Okay? And for the memory is the same actually. So for the whole card, you have this global memory. But on each string processor, the purple box here, inside it, you can also see there is a per block shared memory. So this is also a memory, a temporary memory. So like a cache, but it's a cache managed by programmer, by your program. No, not like the CPU cache. As we all know, we have no control over it. But for GPU, the cache, the shared memory is managed by the user. Okay. So of course, this is one of the important optimization skill we need to learn for GPU programming. Okay. All right, so basically that's just a heads up for the GPU architecture. And as we know, this is a SIMD architecture, so all those cores can supposedly computed at the same time and at a very high, give you a very high throughput. Okay. Right, and this is Xeon Phi, so I will not talk it too much because this here just a picture showing how many cores are there, and as you can see, there's a interprocessor network. So the goal again is try to minimize the communication overhead between those core, right? So you can have a better performance when you do the parallel computation. And as I said, the unique strength of Xeon Phi is it's a standalone processor. You can install your own operating system on top of it. and it has better compatibility to CPU, especially the Intel CPU. Some people would like to use Xeon Phi. All right, and lastly, I would like to show you the architecture, the processor architecture for Sunway Tai Lite. Okay, Taihu Lite. Okay, so this is the processor for China's supercomputer. It was ranked #1 at once. Okay, and the interesting for this one is it's pretty much like the Fujitsu's processor. It doesn't have accelerator. It doesn't need to have an accelerator because its own processor already combined the two processor, kind of processor chip together. As you can see over here, right, its processor already have the slave cores, and they have the master core. So the master core is acting like a CPU, and the slave cores acting like the GPU. And they are even more tightly coupled together on a single chip. So you can imagine, supposedly it can further reduce the communication costs, right? And even between different processor. But of course, it's a new architecture, so it needs a new software stack on top of it, and you need new programming language, etc. So also, still you need to the master core and the slave cores. They still need to communicate through the memory copy, right? So you have the main memory, and you have the MPE. This is another chunk of memory used by those slaves. So you still need to do those memory management and memory operation efficiently in order to achieve the best performance. Okay. All right. So so you can see the trend is clear. People tend to use a SIMD processor. And the biggest challenge you can see is to how to minimize the communication costs and how to optimize the memory architecture or memory bandwidth in order to allow the memory access time to catch up your computing speed. Okay. Otherwise, you will never see its real performance. Okay, the last one is a specialized processor. It's a specialized because this kind of processor can only perform a certain operation or instruction. And of course, it's specialized. So, for those specific instruction and operations, they can gain a lot more performance than the general purpose processor, right? And TPU is one of the classic example and widely used today. And this is specialized for deep learning, as we know, because 80% probably of the computation for deep learning application is doing convolution. So the TPU is specialized for just for convolution operation. Okay, so it's specific design for that single instruction, that operation, and make it become a single instruction, so it can perform that operation very quickly. Okay. We don't give too much introduction to this, so if you're interested in it, we have the link below and you can check it out. Basically, because you only need to design to run a single instruction, so you can hardwire the whole, right, the logic for the processor, so you can do this very efficiently. All right. Okay, so for processing, right, you can see that besides how to parallelize your code efficiently, or how to design a algorithm that that has lower computing complexity, you probably also need to use those processor, those new developed processor, so you can get those computing power. Okay, right? Okay, so now it's 4:20. So we will have a break for 10 minutes, and we will be back at 4:30 and introduce the how the network and how the I/O can also be optimized on those computing systems before we introduce how to analyze the payroll program. Okay, if you have any question, you can feel to ask right now. And if you don't have question, you can put down your hand. I saw a couple of students haven't put down, still raise your hand now. So if you have question, you can just unmute, and if you don't, you can put down your hands now.